Hello, and welcome to my poster, Modeling the Thermal and Chemical Evolution of the Martian Lithosphere Through Time. My name is Rose McWherty, and I'm a master's student at Virginia Tech. The reason I did this study is because there are currently few constraints on Martian evolution. So what we know about Mars, we know from orbital scans, and we know from rover missions and landers. For example, Spirit and Opportunity are two famous rover missions. However, we don't actually know very much about Mars beyond what we've gotten from these types of studies. We do have some meteorites that have come from Mars that we have studied, but we don't actually have any samples that have been returned from Mars, nor do we have the variety of observation equipment on Mars that we do on Earth. And so I did this research in order to help us understand how Mars has evolved over time, and specifically how the chemistry of the crust and the mantle have changed over time. And so this right here, figure 1, is a schematic of the Martian interior. And so we know that the crust is 50 kilometers on average. And we know this because we can actually measure the gravity in a specific area from orbit. And so from those studies, we found that the crust ranges from 3 kilometers thick to over 100 kilometers thick, but on average, it's 50 kilometers thick. The section beneath, which is labeled conductive mantle lithosphere, is the very top part of the mantle beneath the crust. And in this area of the mantle, heat actually moves a little bit differently than in the part of the mantle underneath. So through the entire lithosphere, this mantle lithosphere, excuse me, and the crust, heat rises straight through, and we call this conductive. In the convective mantle, heat actually moves in convection cells or in these circular shapes. And so we see heat rising in this area here, and it's carried over, and then this cool material sinks. And so you end up with this circular convection cell. These convection cells are not drawn to scale, nor is the little Martian lander, the InSight lander, drawn to scale as well. So we use two different methods. We use geochemical and geophysical methods. And the reason we use these two different methods is because they tend to tell us very different things about a system. And we want to know what's actually happening on Mars. So we're using these two different methods in order to combine them and get a better idea of what's actually happening in the planet. And so the first thing we did was we calculated the temperature through the Martian crust and mantle. And so through the top part, the crust and the conductive mantle, we used this equation right here. And we solved for the temperature through depth in billion-year increments. So at 4 billion years ago, 3 billion years ago, 2 billion years ago, 1 billion years ago, and today in the present. These are the numbers that we input into this equation. And we made some assumptions that there are what we call heat-producing elements. And so these are uranium, thorium, and potassium. And so these are elements that are radioactive. And as they produce radioactive decay, they also produce heat. And so what we're looking at is the amount of heat that's being produced inside the planet. After we calculated the temperature through the planet, we then calculated how much melted in the planet over time. And so we used this equation right here, and we used the pressure where the melting began, and we used the pressure where melting stopped, and I'll point these out on a figure in a few minutes. And we use these to calculate how much melt is being produced at a particular pressure and temperature. And then we used some experimental data. So some scientists actually went into the lab and they actually constructed some samples that match the Martian's composition. And so they actually did experiments on these samples in order to see what the compositions of various minerals and melt would be. And so based on this experimental data, we actually produced an equation that actually tells us what the composition of a melt is. And I'll talk a little bit about this in a moment as well. Using geophysical methods, we did the same steps that I just described, but we used a program called SITCOM-S. So our preliminary results, this is a geochemical aerotherm, which is a very fancy way of saying this is the temperature through the planet. And so through the crust and through the conductive mantle, which is the very top part of the mantle beneath the crust, the temperature is represented by this line. And we have temperature in Kelvin, which would be the temperature in Celsius plus 273.15. And we have depth over here in kilometers. We have pressure in GPa. And so this is telling us at a particular depth or pressure, what is the temperature? And these dashed lines represent the bottom part of the mantle, which is the convective mantle. This black line right here represents the solidus. So everything to the left of the solidus line is completely solid, and everything to the right of the solidus is melted. Now there is also a liquidus line that we do not have plotted or calculated. And that liquidus line would act the same way as the solidus, where everything to the left of the liquidus line would be partially liquid, partially solid, and everything to the right of the liquidus line would be completely liquid. So the liquid in this area right here to the right of the solidus line is partially solid and partially melted. It's similar to when you put an ice cube in the sun and you start to get a little puddle of water around the ice cube, but you still have a solid ice cube in the center of that puddle of water. That's the type of material that we see here to the right of the solidus. So this dark line right here represents Mars in the present day. And what's very interesting about this temperature is that we can see in the present day that the temperature never actually gets past the solidus. And what this means is that over the entire planet, on average, there is no melt being produced. Now, we might also consider melt to be magma or lava. So what this is saying is that there is no lava being produced in Mars, and so the Martian volcanoes actually cannot erupt. Now, it's important that we include the disclaimer that this is based on a global average. And if we were to make this type of calculation for the Earth, it would also say that there's no melt being produced on the Earth. And yet we see that there are volcanoes currently erupting today on the Earth. And so this does not mean that there's no melt produced in small local areas on Mars, but it does mean that overall in the entire planet, there's no melt being produced on average. There's not enough melt being produced in local areas to actually change this equation and push it past the solidus. In the past, however, we can see that the temperature actually does in fact cross the solidus. And so what that tells us is that in the past, there was actually possibly a magma ocean. So we can think of an ocean, just like our water ocean, beneath the surface of the planet and made of magma. And so there's a lot of liquid magma inside the top of the mantle in the past. And we don't see that today. And that's what this is telling us. Now we read this, we follow the solid line, and this tells us the temperature going down through the top part of the mantle. And then when it intersects with the dashed line, we pretend that the solid line over here does not exist. We pretend that the dashed line up here does not exist. So for the present day, we follow this temperature curve, and oh, it intersects with the dashed line of the same color. And so now the temperature follows down this path here. Or for 4 billion years ago, the temperature follows this very light colored line, and it intersects with the light colored dashed line of the same color. And so now the temperature shifts and follows this line right here. And so we can see that over in Mars' past, the planet was a lot hotter, and we can see that there's a lot more melt produced, which makes sense because the planet has cooled over time, and as things cool, they don't melt as quickly, or they don't melt as much. This figure right here, figure 3, shows the same thing, but it's taking the results from the sitcom S program that I mentioned above in the geodynamics, the geophysical methods. Now, when we calculated the melt model, what we did was we took data from previous experiments and we fit an equation, and we said what equation would produce these calculations based on these conditions. So this is a regular polynomial equation, f of x, y equals z type of equation. So we put in these temperature and these melt, these pressure inputs, and it gives us the output. So we fit the SiO2 data to this model here because we wanted to show what we did, but we did this actually for several different elements. So we divided these by pressure just to make it a little bit more simple, a little bit simpler, a little bit easier to read. And so we have the data plotted here. These are the solid points. And then these lines represent the model that we calculated that predicts how much of an oxide will be in the melt based on the input conditions. And our result here is this geochemistry and geodynamic melt model results. And what this tells us is how much melt. So F here represents melt. We just use the letter F instead of M. That's just a funny thing about us. And so this is showing us how the melt has produced over time. So this is 0% melt, 100% melt, 4 billion years ago, 2 billion years ago, 0 billion years ago, which would be today at this minute. And then this is showing how different oxides have changed over time. So we can see that there is less silica in the melt. We can see that the iron has decreased a little bit. We can see that the aluminum has increased. We can see that the calcium has increased. The magnesium has decreased. The potassium has increased, both the geochemistry and the geophysics. And the sodium has increased. And of course, we have error. So what this error means is that, for example, this point right here, this is the value that we calculated, the amount of sodium that's in the melt, but it actually could be up here at the very top of this line or down at the very bottom of this line based on the error that's in the calculation. Now, if I want to explain this in simpler terms, then this would be kind of like when you take a bag of marbles and maybe you have red and green and purple and blue marbles all mixed together in a bag. And that would represent our mantle. Now, as things melt, that's kind of like taking marbles out of that first bag and putting them in a different bag. So let's say that what we're looking at is how silica, how the green marbles have changed over time. So what this is telling us is after 4 billion years, how many marbles are in the first bag and how many green marbles are in the second bag. Then we take some more green marbles out, we put them in, and we're looking at the percentage or the concentration of the green marbles in each bag. And so the second bag we could say is our crust, and that's the composition of the crust. How much iron is in the crust versus in the mantle. And so this is like taking those marbles out of this bag. We say, let's take the blue marbles, or iron's red. Let's say we take the red marbles out of the first bag, or that's taking them out of the mantle. Then we put those red marbles into the second bag, into our crust bag. And so we're saying, how has the composition, how is the number of red marbles compared to all of the marbles changed in each bag over time? And that's what this melt model is telling us, but for calcium, magnesium, potassium, etc. So the implications of this project is that we can see that the planet has cooled over time on average. And we've seen that the crust and the lithosphere have thickened over time, which makes sense. As the planet cools, you would expect the crust to get thicker. We can see that the melt production has decreased, which means there's less lava being produced on Mars. And we can see that there's no melt being produced today on average. And what we get from this is we have a better understanding of how Mars has changed over time. We have a better idea of how the chemistry has changed, and we have a better idea of how the temperature has changed. The next steps, the next steps for this project will be to recalculate these aerotherms, and we will do this to account for the calculated crust and mantle lithosphere compositions. And so what this means is we calculated the temperature based on the elements that we thought were in the crust and mantle. But now we see that that has changed from our melt model, based on our melt model. And so we'll take those changes into consideration and recalculate the temperature to see how the temperature changes. We will also refine the error, so we'll just make sure that the error that we have presented here is the most accurate error that we have. And what we want to do is tie these two methods together, because right now, geochemistry tends to tell us one thing about a system, and geophysics tells us another thing about the system. And what we want is we want those two methods to tell us the same thing about the system, because that's when we know that we're actually right. And so what we want to do is take those two different methods and combine them and refine them to see what we need to do to actually know what's happening here. Thank you very much for watching my poster presentation. And if you have any questions, please comment or reach out to me, and I'm happy to talk more about this. Thank you.